A lot of people who are learning about friction for the first time find that static friction is a little bit weird, a little uncomfortable. And that's because this equation, the defining equation for our model of static friction, has a less than or equal to sign in it. Unlike kinetic friction, where you can just find an equation and find a value for the magnitude of the kinetic friction, we get this equation that says that, okay, the magnitude of the force of static friction is going to be less than or equal to the coefficient of static friction, mus, times the magnitude of the normal force. And it's a statement, but this is one of the only prominent times I can think of in physics when you run into a less than or equal to in a clear way like this. And that throws people for a loop. What do I do with that? I mean, the static friction, the kinetic friction equation just tells you here is the magnitude of the kinetic friction force. You just use it. Here, a less than or equal, it could be almost equal, it could be zero, it could be anything in between. Who knows what it is? It's tough. So what we need to do is figure out some strategies for answering the types of questions that come up about static friction. And in my experience, almost every question about static friction that I can think of falls into one of two categories. Maybe every one I can think of falls into one of two categories. Some of them are, does it slip questions. Here's all the information. Now you tell me, will the box slip down this ramp? So in this case, I've got a box of mass m and sitting on a ramp at angle theta. Does it slip if I tell you all the data? Or the other type of question you'll run into for static friction problems is a problem where the question is more, here's the situation, but I want to know what is the maximum angle before it starts to slip? Or what is the minimum force I would need to exert this way to keep it from slipping? That kind of thing. So there are the does it slip questions and the find the maximum or minimum of something questions. And I'll talk through how you solve each one of those. We'll do an example of each type just so you get the feel for it. So first, the does it slip questions. These are actually the easiest ones. What we're going to do is this. If you're given, so here's my full example. In this story with mus equals 0.6 for the box on the ramp, if the mass of the box is 2 kilograms and the ramp is at angle 35 degrees, does the box slip down the ramp or will it stay put? That's our question. So here's what we do. It's really simple. We start by saying we're going to, our strategy, our plan, is to assume no slipping. We're going to assume it doesn't slip, find the magnitude of the force of static friction that we need to make that under that assumption, and then check that defining equation. That's our plan. So let's just do it. Let's do it for this setup. What do I have here? Well, I know that I have, this is a question about forces, so my first step is always to draw a free body diagram. Every single time you start a force problem by drawing a free body diagram. Here's what I'm going to do. I'm going to draw a dot to represent my box, and what do I have? I look at my contact forces around it. Only one point of contact with the outside world, and so at that point there is expected to be a normal force because there's always a normal force when two things are in contact. And then along this direction there's going to be a static friction force. If I'm worried about it slipping downward and the friction stopping that slipping, the friction must be preventing it from slipping downward. So I'm going to draw it this way. It has to be parallel to the slope. The friction force has to be parallel to the slope, but remember, if you guess the direction of a frictional force wrong, you're probably, if you guess the direction of a static friction force wrong in any case, since that you don't know what the direction needs to be a priori, if you draw the arrow the wrong way, it's okay, you'll just get a negative sign for its magnitude in the end, and that you can just say, oh, now I understand what that means. It means I drew the arrow the wrong way. In this case, I'm pretty sure it's going to be the frictional force will be up the slope because we're trying to stop it from going down the slope. And finally, those are the only contact forces. And so the only long-range force acting here is gravity. So I'm going to go ahead and put the force of gravity acting downward. Got that? And on my free body diagrams, when I do these, I always, in addition to the force vectors off to the side, I write down, I either draw the acceleration vector that I expect, or I write down, as in this case, acceleration equals 0. Because I'm assuming no slipping. And so acceleration is 0 in that case. It's going to stay still. So I've done this. I've got this drawn, and as part of my free body diagram drawing process, I guess it's very helpful for me to see where the angles are in that. That's kind of what free body diagrams are for, is to help you visualize those angles so we can eventually write down vector components. So let me dot in some things to find the angle. For example, horizontal is in my reference picture. So that horizontal line is our flat ground, and this is this way, so I know I can put an angle theta right here. I know I can label that angle as I've shown. But then to solve this problem, this is one of those problems, any coordinate system will work, but this is one of those problems that is by far easiest to solve if we use tilted coordinates. Coordinates that line up with, well, what do I usually say for choosing a coordinate system? Your top goal is to make your coordinate system line up with the acceleration. Acceleration 0 here, so that's not relevant. Second goal, make your coordinate system align with forces whose magnitudes you don't know. So here, the normal force and the static friction force would be perfectly lined up if I choose a coordinate system that goes like this. So I'm going to go ahead and call this my x coordinate and this my z coordinate. X is tilted down that way, z is tilted up that way. That's my x and z. They're tilted compared to the usual x and z. I mean, we know that. They're tilted compared to our usual coordinates, but the beauty of this is that by doing this, we will have much simpler equations at the end. If you didn't use tilted coordinates, it'll still work. You'll just have much messier equations to deal with. This is easier. It's worth the effort to get used to tilted coordinates. All right, so what do I do now? I want to label. You can see actually that my normal force is going to be directly along the z component, the z coordinate. My static friction force is going to be directly in the minus x direction, but I need to figure out how my force of gravity fits into the picture. And for that, I guess what I need to do, I need to know some angle relating this vector, which is straight down, to my tilted coordinates. There are lots of ways of doing this. And I've talked about this many times in many ways, but one way of doing it is to say, imagine the coordinates you're used to, like this, and then rotate them like that. This one went up by angle theta. That must also be angle theta. So this angle must be theta. That's one way of doing it. Another way of doing it is to notice that if this angle is theta, then the one next to it over here must be 90 degrees minus theta, because that's a right angle. But then this is also a right angle, so that must be 90 minus theta, or just theta again. So there are multiple ways of figuring that out. Whatever way works for you, more power to you. So okay, however you do it, I know this angle is theta, and I guess the last piece is I want to make sure that I know how to draw this gravity vector, this force vector, as the hypotenuse of a right triangle with that theta inside of it. And that is pretty easy to do. All I need to do to draw it as a hypotenuse is to say, okay, that means I have a line parallel to z going through the tail. I have the z-axis going through the tail. I'm going to draw a line parallel to x, parallel to the x-axis, going through its tip. There is a right angle, because this is parallel to z and this is parallel to x, so it's a right angle, and that's the hypotenuse. Great. All right, so we've got our free body diagram all drawn. We've done what we need to for the free body diagram. And now I can go on and say, how do I solve this? What do I do to solve this problem? And what color do I want to use for this? I'm going to do black. Why not? So to solve the problem, what do I do after I've drawn a free body diagram? The answer is always the same. Every example I can think of, if you're doing problem solving, once you draw a free body diagram, the next thing to do is write down Newton's second law in components. All right, so Newton's second law, remember, tells me that F net is equal to mass times acceleration. That's our story. That's Newton's second law. And so here, I want to write down all my forces, the sum of all my forces, and set them equal to, well, 0, since acceleration is 0. Let's see what that is. So my sum of my forces is F static friction plus F normal plus F gravity, and that has to equal mass times acceleration, which equals 0. So now that's the general statement for this free body diagram. Now let's do it in components. What we have, the force of static friction is all in my minus x direction. So it's going to be minus, I don't know the magnitude, I'm just going to call it minus the magnitude of the force of static friction, 0, 0. I'm using three-component vector notation here. If you're someone who does x hat, y hat, z hat, or I hat, j hat, k hat, cool. But I'm using a three-component vector notation at this point. I've got that. My normal force vector, 3 components, it's all in my plus z direction. So this is 0, 0, and the magnitude of my normal force. That one, those two are the easy ones because they line up with my coordinate axes. It would be much messier if they didn't. Now I just have one that's not lined up. Let's do that. Plus, when I do this one, okay, for me, I always like to think about the signs of things first. So this vector, before I think about any trig functions, I like to think about plus or minus signs. This is more in the plus x than the minus x direction. So I'm expecting a plus up here. I know there's 0 in the y direction for this. And in the z direction, it's more minus than plus. So I'm expecting a minus down here. I've got the signs in by hand, the plus or minus signs in by hand. Now I look at trig functions and I say, okay, for my x component, am I looking at here at a sine or a cosine of theta to give me the x component? Well, this is opposite, and that's the hypotenuse. So in particular, I guess if I label this, if this is the x component of gravity, of the gravitational force, I can write down that the sine of theta is equal to the opposite side, Fx gravity, divided by hypotenuse, the magnitude of the gravitational force. I know that's how trig functions work. And so down here for the x component, it's positive, and it's going to be the magnitude of the force of gravity. I know what that is. The magnitude of the force of gravity is just mg. Mg times the sine of theta. Similarly, this side is going to be my z component, 0 there, and it's negative. I already said it was negative. And this is a cosine function because it's going to be the hypotenuse times the cosine will give me, times the cosine of theta will give me the adjacent side. So minus mg times the cosine of theta. And that has to equal the 0 vector, 0, 0, 0. Cool. Okay, I've got that. This is Newton's second law in components. I've done my next step. But now this is great news because I now have I've got these pieces. Those are component equations. I can just, I guess I could just read them off of here. Once you get used to this, you can just read them off of this Newton's second law sort of 3-component vector notation. But I'm going to go ahead and write it down, write them down as separate equations. I've got here, I almost want to just solve it, but I'll go ahead and write it down. Minus force of static friction plus mg sine theta equals 0. And then down here I have normal force magnitude minus mg cosine theta equals 0. And hey, here's the great part at this point. Let's count something. I have 2 equations here, and I have 2 unknowns. My force of static friction is an unknown, and my normal force magnitude, magnitude is unknown, and my normal force magnitude is an unknown. 2 equations and 2 unknowns I can solve. Let's do it. Let's put this together. In fact, you can see this is the easiest set of equations to solve ever. This just tells me that my force of static friction is equal to, just adding that to both sides, mg sine theta, and my magnitude of my normal force is equal to mg cosine theta, adding that to the other side. So I've got this, and I have those 2 answers. Now all I have to do is put them into this. Again, if you had done this without the tilted coordinates, you would have also had 2 equations and the same 2 unknowns, but they would have been really messy because both unknowns would have been in both equations, and you would have had to solve them more. I mean, it's still just two equations and two unknowns. You can do that, but I like to avoid complicated algebra if I can help it. I make too many dumb mistakes. So, okay, got this. Now, I've done the assume no slipping, that was the A equals 0 part. I've done find the force of static friction, I guess, and N, and I should have said that right here, and the magnitude of the normal force, and find them both. Now I have to check. Let's put it in. Force of static friction. So what do I have? I find here that magnitude of the force of static friction, is it less than or equal, question mark, mu s times the magnitude of my normal force? Well, let's put them in. Force of static friction was mg sine of theta, and I want to know, is that less than or equal to mu s times my normal force, mg cosine theta. And hey, this is one of those nice cases where a lot of things cancel out. It turns out I can divide both sides by m. We know it's not 0. I can divide both sides by g. Definitely not 0. That's kind of cool. The mass and g both canceled out of this. That happens a lot if static friction is the only force, if gravity and static friction and normal force are the only things in there. That is common. So this is reduced to asking a question, is sine of theta less than or equal to mu s times cosine theta? That still sounds messy, and it is. Here's what you do. Just divide both sides by the cosine. Because one of the few trigonometric definitions or identities you should know is that sine over cosine is tangent. Tangent of theta equals sine over cosine, sine of theta over cosine theta. I want to know, is that less than or equal to mu s? So in other words, is the tangent of 35 degrees less than or equal to 0.6? That's my question. Well, this is one we can just type in. I did that at some point. Where did I write this down? The tangent of 35 degrees is, this comes out to be 0.700 to 3 sig figs, I believe. Maybe it was 701, but it's 700. So that means no, it's not less than or equal to 0.6. If the equation fails, that means that you would have needed more static friction than you're allowed to have to keep it from slipping, to keep the acceleration 0. And at that point, you can conclude it slips. So that's how you solve the does it slip type static friction question. You just go through, you assume it doesn't, find the static friction magnitude and the normal force magnitude, and then check it out. Does it slip? All right, got that. The other piece, then, the other version, we're going to be able to reuse a lot of this, is the type 2 thing. In this case, I'll say, okay, if it's slipping there, let me ask then, so example 2, find the maximum theta before it slips. And again, we could say, I could have said if m equals 2 kilograms. I could have left it out. We saw a mass canceled out in this equation. I could have left out the mass here. I could leave it out here. But okay, so find the maximum angle. Okay, it's like, okay, wise guy, if it slips here, how far could we have tilted it before it slips? So in this case, this is finding a maximum of something. What we're going to do is, our strategy here, our plan is assume equality. Assume equality. That is to say that, in our case, the force of static friction equals mu s times the magnitude of that force equals mu s times the magnitude of the normal force. Then once you've done that, solve for our unknown. And why does that work? The idea is that the maximum theta, you imagine that when this is flat, you don't need any force of static. When it's flat, you don't need any force of static friction before it slips. You need more and more and more. The maximum angle will be the one it just reaches before we get our answer. So you assume an equal sign and solve for the unknown. Here our unknown is theta. But that's our plan. Again, assume equality and assume no slip. We're also going, again, you're going to assume it doesn't slip. You're going to assume that you're right on the border before it starts slipping, and you're going to say, where is that borderline? So, in fact, almost all the math we did over here will look the same. The free body diagram looks the same. Here theta is an unknown, whereas here theta was a variable. But you'll notice I didn't plug in 35 degrees in all my work there. That's force of habit, because I've learned as a physicist that a lot of times it pays off to not plug in numbers until your very last step. So the fact that I didn't plug also 35 degrees takes more work to write than theta. But so because I didn't plug it in, I can reuse all this. Now theta is an unknown number, but this equation doesn't care whether theta is a known or an unknown. This equation didn't care whether theta was known or unknown. These equations didn't care whether theta was known or unknown. Where did it come in? In fact, I even had this point where I got to the point where I said tangent of theta, right here. I got to the point, all of this carries over. Tangent of theta equals mu s. That I get right there. I'm just, instead of the less than or equal, I assume an equals. That's the only difference between these processes. Here I had my less than or equal still. Now I assume equality. I put in the equal sign instead of the less than or equal. I've got it now. I've got this as an equal sign, and I mean, at this point it's straightforward. My theta then is going to equal to theta max, if you want to think of it that way. My theta max is going to be the inverse tangent of mu s. So the inverse tangent of 0.6, and when I plugged that in, when I did this earlier, the inverse tangent I get is 31.0 degrees was what I came up with. So we weren't too far off earlier, our 35 degrees. 31 degrees is the answer I come up with for this particular system for my maximum theta. So again, this would have been just as long a problem as this one, but it's the same problem, especially if you didn't plug in numbers first. It's the same problem. All we need to do, we still assumed that it didn't slip. We still used all the same free body diagram Newton's second laws. All we needed to do this time was then, instead of testing an inequality, we used the equality to solve for our unknown. It's a third equation in three unknowns now. Our unknowns were the magnitude of the normal force, the magnitude of the static friction force, and theta were our three unknowns, and this serves as our third equation in three unknowns. So you can imagine you could have done the exact same thing if I had said what would be the minimum mu s, the minimum coefficient of static friction before it slips at angle 35 degrees. I could have asked that question instead, and you would have done it the same way. It would have just, you would have done tangent 35 degrees equals mu s. It would have been 0.7, would have been the minimum. So you can do any number of questions. If I asked, how hard do I need to push to hold it up, to keep it from slipping, I would have had just a second up the slope arrow going. And that would have said how hard I needed to push to keep it from slipping. There are a lot of things like that you could do. But I hope this gives you an idea of the strategies you use for the two different types of static friction questions you can come up with.